This is a gyroscope. Gyroscope is a spinning object that maintains its orientation, that stays upright, or it stays in its main orientation. And the reason it does this is this thing called angular momentum. Angular momentum has a symbol L, and it's equal to the rotational inertia, which is how hard it is to change an object's rotational motion, times the angular speed. So angular momentum equals angular rotational inertia or moment of inertia times the angular speed. And the reason it stays in one direction is because angular momentum is conserved if you don't have an external torque, just like linear momentum is conserved if there's no net external force. So if there's no net external torque on this thing, the angular momentum will stay in the same direction. But it's a little weird. What's the direction of the angular momentum? To know that, we have to think of this thing called the right-hand rule. And the right-hand rule shows the vector direction of angular velocity and also angular momentum. Angular velocity, as this thing is rotating in this direction, around like this, to find the direction of the angular velocity vector, we put our fingers in the direction that's moving, and our thumb will point perpendicular in the direction of the vector. So the angular angular velocity vector, if this is spinning this way, the angular velocity vector is straight up there, okay? And since momentum is the rotational inertia times the angular velocity, the momentum is in the same direction. So when I spin this gyroscope, the angular momentum tends to stay in the same direction if there's no net external torque. So if it's got a lot of angular momentum, it's going to be a much stronger incentive, I'll say, to stay in the same direction. Small forces, small things like friction and mg being a little off center won't mess it up too much. And that's the same reason a bike wheel stays upright. Bike wheel stays like this when you're going very fast, but when you're going slow, there's not a big angular momentum. So it's much easier to fall over. Random torques can make it fall over. If mg is a little off center, boom, it's going to go over. And I'll show you a dramatic demonstration of that. So angular momentum is actually kind of cool because if you think of linear momentum, if I roll a ball, right? Well, conservation of momentum for one object for linear momentum is really dull. If there are no net external forces, then the momentum stays the same. But your mass can't change, right? If I roll a bowling ball, the bowling ball's mass doesn't change. So mv before equals mv after if there's no net external force. That's kind of dull. That just says Newton's first law is true. If an object's moving in a straight line, it'll continue moving in a straight line until there's a net force on it. But angular momentum is different because angular momentum is the product of I and omega. And guess what? You can change your I, your rotational inertia. Here's how. If I'm rotating around this axis, remember that rotational inertia has to do with how far away mass is from the center. So if I'm tight in like this, I've got a very small rotational inertia. It's easy to spin me. If I'm out like this, I've got much bigger rotational inertia. It's harder for somebody to change my motion. Let me show you a demonstration that worries me because I'm not 20 years old anymore. I've got a rotating platform here, okay, and I hope it'll work, and I hope I don't hurt myself. I'm going to give myself, better move over here. I'm going to give myself a little push, and I'm going to get myself rotating. Okay, so I have certain rotational inertia, and I had an angular velocity. Right-hand rule tells me the direction of that vector is up. So it's certain angular momentum. Now, if there's no net external torque on me after I get going, angular momentum should be conserved. So watch what I'm going to do. I'm going to have big angular rotational inertia. small small rotational inertia. Okay, let me go in the other direction. Let me go from small to big. Small, big. Okay, and I apologize because my balance is not that great. But what happened was when I had small rotational inertia and I increased it, the angular speed decreased because the momentum was conserved. Let's take a look at that real quick. Okay, so when I had a small rotational, let's do it in reverse. When I had a big rotational inertia, 5 kilogram-meters per second squared, and my omega was 2 radians per second, then my angular velocity, angular momentum was 10 kilogram-meters squared per second, and that's the unit, because radians doesn't really count. It's dimensionless. It's meters per meter is a way of thinking of it. So afterwards, I had the same angular momentum. There was no net external torque on me, but I decreased my rotational inertia. And so my omega, 10 divided by 4, went up to 2.5 radians per second. So you see this all the time. You see this with ice skaters. They spin and then they pull their arms in to spin faster. They decrease their rotational inertia to increase their omega. You want to think of it like, let me draw the variables bigger. Here's I, and a small omega has to equal a smaller I times a big omega. Okay? This happens with divers. Divers they give themselves an angular momentum, and then they decrease their rotational inertia around that axis, and that increases their angular speed. Cats can actually turn around in air, and I believe that that's based on their ability to change the rotational inertia of the different parts of their body. If these are the cat's legs and they're upside down, one thing they can do is stretch out this lower rotational inertia here, makes it easier to turn. This one will turn a little bit, but not very much. Then they can stretch that out, bigger rotational inertia, stretch this out, smaller, rotate that around. I'll show you, I can do that here. Okay, I've got big rotational inertia at the top part of my body, little rotational inertia at the bottom part. So when I move this part over, thinking of my body as two halves, the other half moves more, okay? Now, I want to show you how this works with something more complex. First of all, we've got a bicycle tire here, a bicycle wheel here, and I've got it hanging from the ceiling. Something very strange happens with this, and I'm going to show you how the math, actually I shouldn't say the math, how the directions work out in a moment. But I'm going to give that thing a spin, okay? Give it a spin, and well, look at this. We've got two forces. We've got mg, and we've got this tension here. And they don't line up, so if I let it go, there's a torque, and it makes it droop down. Okay? But if I give it a good angular speed, and I'm going to do it in this direction, which means the angular velocity and angular momentum will both be in this direction, it should stay more upright. Okay? It wants to maintain that direction. The problem is there is a net torque, and I'll show you how that affects the direction of the angular momentum. Here we go. Wow. Whoa! And it should be just rotating around. So what happened when I give it a big angular velocity and the angular momentum is in this direction? It would stay in that direction. That's what happens when you're riding a bike, because there's no torque over here. Okay, there's no net external force trying to make it twist. But what happens here is with that torque, this ends up, it's called processing around in a circle. So it's a very, very different motion than we're used to. And I want to show you how that works. how that works. And over here, what I've got is I've got the tire, the wheel, rolling around. And this is a little complicated, so bear with me. This is going to be a long video. Okay, so I gave it a velocity in this direction. Okay, we're kind of looking face on. That means the angular momentum right-hand rule is in that direction. The angular velocity is in that direction. The angular momentum, which is I omega, and omega is a vector, they're in the same direction. So that's the direction of the angular momentum. Now what's going to happen is I apply a torque, okay? And the torque, remember that was held still. The torque direction is R cross F. Torque equals R cross F. Okay? R cross F, the right-hand rule says the torque is out of the board. And if you're just doing AP Physics 1, you don't care about this too much, but I want to show you how this works. So the torque is out of the board. The symbol we use for out of the board is that right there. Okay, it's like an arrow coming at you. If we wanted to look down on this, it would look like this. If we're looking down on the wheel, the direction of the torque, again, is in this direction. That's the torque direction. The omega is, or the L is in that direction. Okay. Now, what happens is, just like change in momentum for impulse is force times time, change in angular momentum is torque times time. Okay, so in this case, the change in the angular momentum will be the same direction as the torque. Well, the torque is in this direction. Let's do it with the wheel here. The torque is out of the board. The torque is in this direction, so the omega will start turning towards that direction. Okay, and that's why the wheel did this when we let it go. It rotated around the rope. Seen from the top, the torque's in this direction, L's in that direction, so L's going to start turning like that. And it really follows, the wheel went around and around that way. And a really clear example of this is if I plug in this device that I have, that, pardon for the time, this is a device that I have that, and I'm going to have to move it. This is, wow, look at that. This is a device that is just a big, heavy disc with a whole bunch of independent bearings. Okay. And the motor is getting it spinning and giving it angular momentum. And the angular momentum is in the direction of that arrow, which is kind of handy. Now watch what happens if I apply a torque here. The angular momentum in the direction, if I apply a force. If I apply a force here, R, F, down. So when I push in that direction, it goes down as a function of the torque and the cross product, the torque changing the angular momentum. Okay, if I push this way, well, you'd think it'd go down too, right? Nope, goes up. So if I apply a constant force in this direction, it just keeps going down. So I'm hoping this helps you see, first of all, that it's hard. We're very complicated. We're talking about three-dimensional vectors all over the place, or three-dimensional vectors and three-dimensional vector math. But the basic concept of why these spinning things do what they do is all based on this conservation of angular momentum. This was for one object. I'll do another video that has two objects in it.